Hey everyone, and welcome. Today we're diving into something really cool. It's a story about how a super old idea, I'm talking 60 years old from the very beginning of computing, is now fixing one of the biggest headaches in modern AI. And the result? It's making everything from chatbots to the coding assistants we all use up to 4 times faster. Pretty wild, right?
But before we get into the solution, let's talk about the problem. A problem I am sure you felt. You know when you're using a chatbot and you ask it something and you just get that little pause, that loading icon? Or, hey, if you're a developer, you definitely know how eye-wateringly expensive it is to run these big models. So what gives? Why are they so slow and pricey? What's actually happening behind the scenes?
Now, your first guess might be, oh, the GPU just isn't powerful enough, the big chip doing all the heavy lifting. But surprisingly, that's not really it. The real problem is a lot more like a giant traffic jam, but it's happening inside the GPU's memory. So it's not about the speed of the engine, it's about not having enough road.
Okay, so if there's a traffic jam, where is all this precious memory going? This chart gives us a clue. See that huge chunk, about 65%? That's the model's brain, basically, all its core knowledge. But then, look at this other big piece, taking up more than 30%. It's called the KV cache. And this thing, this dynamic, constantly changing piece of memory, well, that's the source of our gridlock.
All right, so let's dig into that. What exactly is this AI memory bottleneck? What is this KV cache thing? And why is it such a troublemaker? Probably the easiest way to picture the KV cache is think of it as the AI's short-term memory. Like its working memory. Every time you have a conversation, it's storing the key points, the context, in this cache. That's how it remembers what you just said. Without it, every single reply would be like starting a brand new conversation. It would have no idea what you were talking about. Okay, now this is where it gets kind of crazy. This chart shows just how inefficient the whole process is. See, of all the space that's set aside for this super important short-term memory, get this. Current systems only use about 20 to 40% of it for actual information. The rest of it, that massive slice of the pie, is just waste. It's lost to a problem called fragmentation. So why? Why is there so much waste? Well, this diagram explains it perfectly. The old way of doing things is just way too cautious. For every single question you ask, the system sets aside a huge single chunk of memory, a chunk big enough for the longest possible answer it could ever generate. But think about it. Most answers are short, right? So all that extra space it reserved, it just sits there, empty, and totally unusable by anyone else. It's like booking a whole movie theater for yourself just in case you invite friends, but then you show up alone. And hey, don't just take my word for it. This is a direct quote from the research paper we're talking about today. It shows that sometimes, almost 80% of this critical memory is just gone, wasted, just sitting idle. Okay, so how do you fix a problem this fundamental? Well, the answer is so cool. It doesn't come from some brand new futuristic tech. It comes from looking backwards to a brilliant idea from the very history of computer science. Way back in the 60s, right? The people building operating systems had a very similar problem. And their solution was pure genius. They called it virtual memory. Here's how it works. A program asks for a big, continuous block of memory. But the operating system, behind the scenes, is super clever. It breaks that request up into tiny, fixed-sized pieces called pages. Then it just scatters those pages wherever there's an open spot in the actual physical memory. The program has no idea. It still thinks it has its one giant perfect block. And that is the light bulb moment. That brings us to the big breakthrough. Some researchers thought, hey, what if we took that same 60-year-old idea of paging and applied it to the AI's memory? And that's how they came up with a new algorithm they called PagedAttention. Right there. That's the core idea. The question that changes everything. What if we stopped trying to find one massive, perfect parking spot for the AI's memory and instead just treated it like an OS does, breaking it up into little pieces that can fit anywhere? And that's precisely what PagedAttention does. You can see it in this diagram. The pieces of the AI's conversation, its memory, they don't have to be neighbors anymore. They can be stored in all these separate little blocks, wherever there's space. And just like that, the whole waste problem, gone. So there's this system called vLLM that actually does this. And it's so much smarter. Instead of booking that whole movie theater up front, vLLM just gives the AI a new seat, one at a time, only when it needs it, as it's generating text. No more reserving memory for a giant essay when the answer is just going to be, yep.
But here's the thing. This isn't just about cleaning up the memory and being more efficient. No. This smarter way of handling memory unlocks a whole bunch of powerful new tricks that make the entire AI system faster and, well, smarter. Okay, check this out. Let's say you ask an AI for 3 different versions of an email based on the same instructions. The old, wasteful way would make 3 separate full copies of your instructions in memory. Total waste. But with vLLM, all 3 of those requests can share the memory for the instructions. And only when their answers start becoming different does the system make a new copy, just for the part that's changing. It's a classic, beautiful trick, again from operating systems, called copy on write.
And that's really just scratching the surface. This new flexibility opens up so much more. Now, systems can explore thousands of possible answers at the same time. They can get a head start on common questions by preloading them, and they can even handle a whole bunch of users with totally different requests all at once, in the same batch. It's a huge deal. All right, so the theory is awesome. The new features are cool, but what's the bottom line? What does this actually mean in the real world? Let's talk about the payoff. 2 to 4 times. That's the performance boost we're talking about. Throughput here, how many requests the system can handle. This isn't some tiny 5% improvement. This is a massive, massive leap forward. And here's the proof. This chart, straight from the paper, shows it plain as day. Look at vLLM compared to other top-of-the-line systems. It just handles way more requests, more users, faster service, all on the exact same expensive hardware. So what does this all mean for you and me? Well, it means the AI tools we use every day can get faster, feel more responsive. For the companies paying the bills, it means their costs go way down. But the big takeaway is this. You can serve 2 to 4 times more people using the exact same hardware. That is a game changer. And that leaves us with this one last kind of mind-blowing thought. This huge leap forward in AI speed, it didn't come from some crazy new invention. It came from looking back 60 years and dusting off an old, brilliant idea. It really makes you wonder, right? How many other amazing solutions are already out there, just hiding in old computer science textbooks, waiting for someone to connect them to the problems of tomorrow?